So my topic is facial reduction, and I've put down applications to matrix completion. So this is something that I've sort of just started doing, so I'm sort of taking a gamble here I was hoping that there are some experts in the audience and they can see what we've done and maybe I can get some feedback. So this is sort of very, very new, and maybe it's well known or not. So I'm going to be talking about facial reduction, and it of course is related to the Slater constraint qualification, which is the existence of a strictly feasible solution, and in some sense it's at the heart of convex optimization. So what happens if you have an optimization problem, a convex optimization problem, and you don't have Slater's condition? Well, the first order optimality conditions may fail. You can have duality gaps, so you don't even know that you're solving the right problem. You'll be solving the dual instead of the problem you want to solve. Small perturbations can result in infeasibility because you don't have any strictly feasible points. And a lot of software packages are going to have trouble because of this. Even though this problem, it has been shown, especially there's a few papers recently, that Slater's condition holds generically. But this is a very common phenomenon in many different areas of mathematics, especially, I think, optimization. And as I mentioned earlier, for example, differentiability. If you've got locally Lipschitz functions, then Rademacher's theorem tells you that the functions are differentiable almost everywhere. So you think if you're running an optimization problem, the optimal value function, well, it's going to be differentiable. The chances are probability 0 that it won't. Except in practice, it always happens pretty well. It almost always happens that your objective function is not differentiable. So the same thing seems to happen with Slater's condition. It holds generically, but there's all sorts of problems where especially in the work that I've been doing, I've been bumping into where Slater's condition fails. So I'm mentioning matrix completions first and compressive sensing, because I'm hoping I'm going to get to that. And Nathan already talked about the sensor network localization. I'll mention a little bit as well and probably run through it rather quickly. The Euclidean distance matrix problem, the problem that so many people were talking about here with rigidity. Polynomial optimization, I think Pablo will be talking a bit about this, but I'm not sure if it's going to be the same slant, but I've been working on some problems related to polynomial optimization, and Slater's condition fails there. A lot of molecular conformation, protein folding problems when you have rigid bodies in the protein. This essentially means that you're losing Slater's condition. The quadratic assignment problem, if you look at the semi-definite relaxation for the quadratic assignment problem, Slater's condition fails. And then you go and you can apply this concept of facial reduction. Do it very carefully and rigidly because you can exploit the structure of the problem, so you can avoid this Slater's condition problem. But what's even more interesting, this is what we've done recently, I'm not going to have a chance to get to that, is that the facial reduction really works well for certain solution methods. For example, ADMM. We've been using ADMM with facial reduction for the QAP. And so facial reduction, what it does is it replaces the big matrix for the problem with a smaller one and guarantees Slater's condition. But what we've been doing is keeping the big matrix, and that allows you to add greater or equal to 0 constraints and less or equal to 1 constraints. So it allows you to add polyhedral constraints, which within SDP, semi-definite programming, is usually very expensive. But by doing this facial reduction approach, it essentially, you get it for free. So we've been doing that for the QAP, quadratic assignment problem, the graph partitioning, again, semi-definite relaxation, and it's been very, very successful. And also the second lifting for the max cut problem. It's a very interesting problem. Of course, this is what put semi-definite programming, I guess, on the map, the Gomez-Williamson result where the semi-definite relaxation is so strong. Well, if you do one more lifting after this famous Gomez-Williamson result, and you start solving these problems, essentially, if you just take random problems, you will never find a problem where you don't find the optimal solution. So you may think this proves P equals NP, except if you go and you take some very special graphs, then you find that it's not always true. So these relaxations are very, very powerful and semi-definite, and the facial reduction really fits in well with it. So in this talk, I'm going to concentrate on semi-definite programming, looking at facial reduction, and specifically I'm going to look at two ways of looking at facial reduction. And I'm in the middle of, with Dima Itsky, we're writing up a little survey, so this should be finished within a week or so, and we'll be posting it. So this talk is very much based on this survey paper that we're writing. So let me do something very similar to what Nathan did in his talk. I'm going to start with linear programming. I've sort of reversed roles. I'm calling the primal of the LP in this form and the dual in this form. That's a little opposite to the usual form. And this is the theorem of the alternative. This is sort of it's a Farkash lemma essentially. And it says that if you have a Slater point, so exactly one of these two conditions holds. If Slater's fails, then you can solve this problem, and you can find a Z, which is equal to A transpose Y for some Y. It's greater or equal to 0. And it satisfies Z inner product any feasible point is equal to 0. So it's an exposing vector for all feasible points. So essentially, if Slater condition fails, then you can find this exposing vector. So this is very similar, if not the same, example that Nathan put up, but some of you weren't here. So this is a linear programming example in 5 dimensions. So we're minimizing this simple little 5-dimensional linear program. And if we go and we add the first two constraints, which is equivalent to multiplying by Y transpose, that's the Y in the theorem of the alternative, then we get this equation over here, and because all the coefficients are positive, well, we know that this forces x1, x4, and x5 to be equal to 0. And so this puts us into a smaller face, namely the face given by x2 and x3, and all the other variables are 0. And it also means that there's fewer constraints. So this is the problem. So back in a long time ago when I first met Bob Vanderby, I was here on sabbatical. This was when the big splash came out with interior point method, and OB1, which was probably the first successful interior point code, was developed in this lab. Well, one of the people in the lab was working on this OB1 code. And one of the big splashes for interior point methods was large back then was maybe 10,000 variables. I'm not sure, maybe somewhat bigger, but not too much bigger. And then suddenly it went to 15 million. But Lustig told me the secret. And the secret was they did a lot of pre-processing before. So it was always a little bit sneaky. So pre-processing is something really important. Identifying variables which are identically 0 on the feasible set is a very important step in software codes, linear programming codes. And there are several other types of pre-processing steps that are very important. Okay. So again, this is Slater's condition, that the theorem of the alternative that I mentioned. And I just want to look at it again in a very specific way. So if we so I'm looking at this time at the primal. Okay, so there's the Slater condition for the primal, and suppose this is going to be the theorem of the alternative for it, and suppose that we can find this D, this exposing vector, which is not equal to 0 over here. Then we can take the components of this D which are positive, and we can use the result that we said that this di times the slacks have to be equal to 0. So it forces these slacks to be equal to 0. So I'm using this little bit of notation here. So y is now a feasible point. And the indices I, where this has to be equal to 0, I'm saying I is in P E. So the E stands for equality. Okay? So the point is that we started off with a bunch of inequality constraints, but some of the inequality constraints are forced to be equal. Okay? So these are implicit equalities. So I can now separate that into two parts. So this is what I've done over here. I've separated, so the L stands for just less or equal to what we had before. So there's got the L. And I've put the little e for the implicit equalities. And what I'm doing is I'm taking the implicit equalities, I'm making them equalities. So this is equivalent to the original problem. And then this ends up being the dual problem. Because if we take a linear programming problem here, we end up getting this dual. And you can see that it's slightly different. This variable is no longer non-negative, it's now free. Because these inequalities became equalities. So this process essentially regularizes the original LP by separating the implicit equalities to explicit equalities. This is how you would regularize a linear programming problem. Okay? So this means that the generalized Slater's condition holds. And as we saw before, some of the constraints the equalities become redundant. Whoops, when you do this. So some of these equalities become redundant. If you remove them, then this thing that you have left becomes surjective, and then you end up getting something called the Mangasarian-Frumovitz constraint qualification. So in optimization, it's well known that Mangasarian-Frumovitz is equivalent to the fact that the dual optimal set is compact. Okay? So interior point methods converge to the analytic center of the primal dual optimal set. So if you're doing an interior point method, and if Slater condition fails, or if Mangasarian-Frumovitz fails, then one of the optimal sets, the dual optimal set, will be unbounded. So the interior point method for one side is just going to go off forever. And it's going to end up with a lot of numerical issues. So doing some sort of regularization like this is very important for optimization code. Okay, so what about the general convex problem? So I'm taking a linear objective just because we don't really have to worry about the objective function. I've got a convex inequality constraint. So g of y is just a vector of convex functions. And I've reversed the usual reverse m and n. Usually n is the space for x, but I've just reversed it because of the reverse in the duality way we're looking at it. Okay. So Slater's condition for this problem is there's a y hat, so that gi of y hat is less than 0 for all I. And that implies Mangasarian-Frumovitz. So if you have a Slater condition for this original problem, everything is good and Mangasarian-Frumovitz holds. But you can prove that if Slater's condition fails, then there has to be some inequalities that are implicit equalities. So you can replace the inequalities by these equality constraints. So I can do the same thing I did for the linear program. I can call the indices for the implicit equalities as PE, and the other one PL. And so I divide the constraints into two parts. And I can rewrite the problem. Now, I'm going to do it in a very special way. I'm going to define f to be equal to the set of all z so that the zi's are equal to 0 for the indices for the implicit equality constraints. Okay? So if we rewrite the original problem, but we remove the implicit equalities and we just replace it by this set fe over here. Fe is defined by the set of all y such that GE of y is equal to 0. So these are the implicit equalities. So it's really surprising that this Fe is actually equal to the set of all y, where this is actually less or equal to. So this is actually a convex set, because these, of course, are given by convex inequalities. And Slater's condition then holds for the regularized problem. That means there exists a y hat in this set Fe such that the other constraints are satisfied strictly. Right? This is equivalent to something which was studied in the, I guess, in the 70s, and this is called the BBZ conditions. So this has been Israel Ben-Talon Zlobec, and the first author has just walked in, so he's actually here. So this was started quite a while ago. I think maybe due to lack of time, I'll just skip this, but this is one way to, there's a special subset of functions where this is very, very elegant and can be applied very nicely. Okay? So the important thing that I introduced here is this minimal face, F. Okay? So you can rewrite the original problem using this minimal face by replacing this partial order, the less or equal to 0, using this minimal face, just like we could for the linear programming problem. Okay, this is a little bit of a heavy slide here. I'm now looking at the total generality for this problem. So this is called the abstract convex program. We're minimizing a function f of x, subject to g of x less or equal to 0, and x is in a convex set. This g is what's called k-convex. So k-convex means that g is convex with respect to the partial order given by the cone, the convex cone k. So the partial order given by the convex cone k means a is less or equal to b if and only if b minus a is in the cone k. And strictly less than means b minus a is in the interior. So Slater here means there exists an x hat and omega subject to g of x hat is in minus the interior of k. Okay? So in notation, this is g of x strictly less than 0. So this, I think, is for people in optimization. So just something which you might take a note. I'm not sure if you're aware of this Slater condition. There's no need for any interior here, or relative interior. Okay? This is Slater's condition for the abstract convex program. And this guarantees strong duality. Strong duality means the primal and dual have the same optimal value, and the dual is attained. So there's a zero duality gap, and the dual is attained. Okay, so one of the things that's very useful for, I've already mentioned the face, and Nathan mentioned it in his talk. So one thing that's useful is faces of convex sets. Okay, so here's the general definition of a face for a convex set. I guess everybody's sort of seen this already. And this is the definition of a face for a convex cone. Okay? If you take 2 points in K and the sum is in F, then both of the points came from F. Okay? And the polar cone or the dual cone is just defined in this way. The inner product is greater or equal to 0 for all elements in the cone. And this is the conjugate face of a face. It's just F conjugate is the intersection of the dual cone with the orthogonal complement of the face. Okay. So please stop me if you have any questions of any of this. So properties of faces. One of my favorite properties. A face of a face is a face. Intersection of a face with a face is a face. And if we take any set C, convex set C and K, then the smallest face containing C, call it the minimal face, and it's the intersection of all the faces containing C. Okay? And if we have a face of K. It's called an exposed face if there's an element in the dual cone where F is equal to K intersect the orthogonal complement of that. That's often called the exposing vector, phi. Okay? And the conjugate face is always exposed by every element in the relative interior of the face. So the SDP cone is very well studied, known, and it's got a lot of nice properties. So it is facially exposed. Every face is exposed, just like Rn plus. And it's a proper closed convex cone. It's also self-dual. So it's got a lot of nice properties. It's been studied for many, many years. In fact, there's an old paper by Bonenblust in the 40s that studied the properties for the faces of this cone. Okay. So let's look at the abstract convex problem. So this is a result I worked on with John Borwein long time ago. So if you remember, in the convex case, it was quite complicated. In the linear case, it wasn't so bad. It was quite complicated to regularize the problem because we had to find this set F equality, the equality set where the implicit equality constraints were equal. However, for this problem, we don't have to do that. Okay, so for the semi-definite program, we don't have to do that. But first, let's take a look at this more general problem. So this is the general abstract convex program. So what do you do to regularize the problem? All you do is you change the cone K with the minimal face. So it's a real trivial statement. When you do that, this problem is guaranteed to satisfy strong duality. So it has no duality gap, and the dual is attained. It has Lagrange multipliers. Okay? And there's something very important about this, doing it this way, and we're going to see that when we do the SDP, is that it's a proper primal dual pair. So the dual of the dual gives you back the primal. Okay, so this is one other thing that may, just to show you how, at least algebraically, how easy it is to get an algorithm to find the minimal face. So again, Kf is this minimal face. And if you have a feasible point, then all we have to do is solve this system over here. So this is omega minus x bar polar. This is the subgradient of the inner product of phi with g of x bar. So we have to find a phi so that this set is not empty. Phi has to be in the dual cone, and then this complementary slackness condition has to hold. If we can solve this for phi, then phi is an exposing vector. So phi perp intersect k exposes the minimal face. It doesn't necessarily attain it, but at least it's getting closer to getting there. Okay? And the proof is really simple, as you can see over here. This is a convex function on omega. So this condition here is sometimes called the Rockefeller-Pshlenishny condition for optimality. So it tells us that we have x bar as a global min for this convex function on omega. So what does that mean? Well, it has to be 0, and we squeeze it in. So this tells us that we have the complementarity, and we get the exposed face. Okay, semi-definite programming. So one of the nice things about the semi-definite cone is that it's such a simple cone to work with. It's very similar to the non-negative orthant. So this is some work that was done, again, I mentioned Bonenblust in the 40s, so it was known all the way back then. So if we take a semi-definite matrix and we take the spectral decomposition, so this D plus is positive definite. It has rank R, so that's the rank of X. These are the eigenvectors. P are the eigenvectors for the positive eigenvalues. These are the eigenvectors for the 0 eigenvalues. Then the range of X is given by the range of P. The null space of X is given by the range of Q. And the face of X can be expressed in this way. So this is why we call it replicating, just like the non-negative orthant. Every face, if we forget the P and the P transpose, it's a congruence of a smaller dimensional SDP cone. And as well, we can write it in terms of an exposing vector given by the Q, which is for the null space, in this way. The QQ transpose is a matrix, and it's an exposing vector for this face. It gives us the face exactly. Okay. And so, and this is if we wanted the conjugate face, we would get it this way. So again, just to summarize, this is another way to express the face of X. And this is a couple of ways using the range and the null space representations. And we also know that the relative interior of every face is obtained exactly when the ranges are equal. Okay, finally, SDP. So this is the definitions for a primal dual SDP. Again, there's the cone, Sn+, it's non-polyhedral, so polar, facially exposed. There's the primal problem. I'm writing it like the abstract problem, using the adjoint of the linear transformation A. And here's the dual problem, and this is the linear transformation A acting on X, and X is a positive semi-definite matrix. Okay, so here are the definitions. A is a linear map. A star is the adjoint. And this is the concrete way of looking at things. Every linear transformation on the semi-definite cone can be written in this way explicitly using symmetric matrices A sub I. And this is how to write the adjoint. It's just a linear combination of the A sub I's. So here's the theorem of the alternative that we saw before for linear programming, but for SDP. And the same thing works. The D here is going to give us an exposing vector. So if we get a D which is not 0, it exposes a face. And so we get that ZD is equal to 0, or equivalently the trace is equal to 0. So this looks just like the linear programming theorem of the alternative. So I guess one thing I should emphasize, well, I will in a minute. Okay. Okay. So here's the regularized form. What do? Just like for the abstract convex problem, all we do is replace the cone K here by the minimal face. So it's a very, very simple regularization. So if we can find the minimal face, then you can regularize the problem. So here's where I wanted to emphasize. If you think back on the convex case, we don't have to worry about the equality set. The equality set is not needed here. All we have to do is do this replacement. Because of the linearity that's hiding, this is all that one has to do. Okay? So FP is, again, the minimal face of primal slacks. So this is how we define the minimal face here. So here we have strong duality. Here's the dual problem. The FP becomes the dual cone FP star. So FP is a face of the cone, of the semi-definite cone. So FP star is going to be bigger than the semi-definite cone. And there's all sorts of work on how to find this expression here. Okay? So here's the statement of strong duality. We have these equalities. The regularized problem is equal to the dual of the regularized problem, and it's attained. And the dual of this problem gives us this problem back, because all you do is take the dual of this dual, and F star star is just F. So we just get this problem back. So this is one of the reasons why this dual is so useful. So this is view 1 for facial reduction. So suppose that we have an exposing vector. We did this algorithm. We found an exposing vector. So the trace of Zx is equal to 0. Equivalently, for semi-definite matrices, this is equivalent to the product being 0. And then we use the spectral decomposition. we find the range of P to be the null space of Z, then all we do is we make this substitution. So the problem, all we do is we take X, we just replace it by this, and then trace is commutative, so we just move the P's around. So we have a new smaller problem. R is in this new smaller space. The objective function is smaller. The objective function is smaller because this matrix is smaller, and each of the constraint matrices are smaller, and this symmetric matrix is smaller. Okay? And then here's a definition that has come up in the last few years. The minimum number of steps that it takes to get Slater's condition, and at each step you're finding a maximal exposing vector Z, is called the singularity degree. Okay? And this has come up already, but I'm going to be talking more about this singularity degree. Okay? So one of the things about Slater's condition so far is, okay, Slater's condition is bad for numerical accuracy. Let's get rid of it, and let's have algorithms behave better once we get rid of it. But there's something called the singularity degree, which seems to have some very interesting theoretical properties as well. And Shinji will be talking more about this on Friday with respect to matrix completion problems. So this is view 2. This is sort of interesting and not obvious for people who don't do semi-definite programming. Maybe it is obvious for the audience here. If we find an exposing vector, then we get a face, right? And of course, what we want to do is we want to find the intersection of faces to regularize the problem. Take the intersection of 2 faces, 3 faces, etc., right? Well, the intersection of faces is just Sn plus intersect the summation of the exposing vectors. The sum of exposing vectors becomes an exposing vector for the intersection of the faces. So this is view 2 of, it's a very, maybe a simple statement, but as Nathan showed in some of the numerics that he was doing, it really helps when we want to avoid noise in our data.
But geometrically, this holds in, for example, polytopes and polyhedra too, right? Or
yes.
Yeah.
I
mean,
so for the non-negative orthant.
Sure.
Yes. Yeah. That's true. Yeah. Okay. So here's a sort of a little overview of this singularity, of what happens with the singularity degree, and sort of the theorem of the alternative that we've been talking about. So just a little summary. So vector V exposes a proper face of the image. So this is sort of connected to another view of trying to find the exposing vectors. So instead of looking at the SDP space, we're taking A of the cone. So this is just a general problem. It doesn't have to be the SDP cone. Okay, so we're trying to solve AX is equal to B, and X is in the cone. It's just a feasibility problem. So vector V exposes a proper face of A of K containing B if and only if B satisfies this condition here. A star of E is in the dual cone. Okay? And the following is always true. So if we find a face in the image, then we can go back and get the proper minimal face for the original problem. Okay, so this is sort of a basis for the algorithm that we're going to be looking at. So this is a further just the explanation of what happens there. So W exposes a face in the image if and only if, when we go back with the adjoint, it exposes a face for the original problem. C is the cone that we're talking about here. Okay. So as a corollary to this, if Slater's condition fails, then the singularity degree is 1 for the system above, if and only if the minimal face is exposed. Okay? So we can find the exposing vector right away, and we can we can regularize the problem in one step. The singularity degree is 1. Okay. In general, you can have n minus 1 iterations to solve. It may take up to n minus 1 iterations to solve to get Slater's constraint qualification. Okay? And so every time we have to solve a system like this, we have to continue, right? However, that system is equivalent to this auxiliary problem over here. So we've rewritten this system with minimizing a scalar delta subject to norm. So this is A of D over here. We're trying to squeeze that to 0. We're trying to squeeze CD to 0. So this is less or equal to delta. And the trace of D is normalized in this way, and D is positive semi-definite. So if this problem is 0, then Slater's condition holds. And if the minimum for this is not equal to 0, then we can find it, then D provides us with an exposing vector. So this is the algorithm that we've been using to try to regularize STPs for the general case, and we have a proof that this is backward stable. Okay, so it doesn't, it'll always solve a nearby problem. So it's a backward stable algorithm.
What does it mean to say that you regularize on the trace of D equals to square root of n?
I don't want D to be 0, because otherwise it's a homogeneous problem, and it'll always go to 0. Sorry?
Why square root of n? Could any value
It's just the norm, because the identity. Yeah. Yeah. But it could be anything. You're right. Yeah. Okay. The other. So one of the. So this is sort of. What's interesting here is it's backward stable for one iteration, right? So you would think. So k equals 1 is really special in some sense, right? Because you can prove backward stable for one iteration. But then after you do the substitutions, you're back to where you started. Why can't you do the same thing again, right? So what's interesting is that what we proved, so k equals 1 is really special. So if k is equal to 1, then so strict complementarity holds for the original problem if and only if k equals 1. Now, if you have a semi-definite program, so this is one of the things that people, for linear programming, there always exists a strictly complementary solution, right? But in semi-definite programming, that's not true. So in semi-definite programming, if you don't have a strictly complementary solution, then your Jacobian at the optimum is going to be singular. So you can go and apply primal dual interior point methods, but your Jacobian eventually is going to get very, very ill conditioned. There's not much you can do about it. So it's sort of, in the literature, people say, well, if Slater holds for the primal dual, I've got a nice problem and everything is fine. But strict complementarity is another thing that can go wrong and something that's important. So this is sort of interesting that if k equals 1, you do get strict complementarity. So k equals 1 is very, very special. If k equals 2, it's not necessarily true that we can regularize the problem numerically in a stable way. But if k is equal 1, you can. So problems where Slater's condition fails, but k equals 1 in some sense, are still stable problems. And every linear program, k is equal to 1. You can always apply the theorem of the alternative, and in one step, get Slater's condition. So here's another little theoretical. So this idea of calling this the singular degree of singularity came up in a paper by Sturm in 2000. So what he proved was the following over here. So if we're given an affine space V, And the problem is to find the a point in the intersection of the affine space and the semi-definite cone. So then this pair is 1 over 2D Holder regular with displacement, where D is the singularity degree of this system, this feasibility system. Okay, so what is Holder degree? Okay, so this is the definition over here. Okay, so we have that for all compact sets U, there exists a constant such that, so the distance from X to here, which is in some sense telling you how hard the feasibility question is less or equal to a constant times the distance to the power gamma of X just to the subspace, which is going to be a simple problem, plus the distance to the power gamma of X to the semi-definite cone, which is a simple problem, right? So the problem that you're trying to solve, the distance here is less or equal to some constant times the sum of these two simple distances, okay? So that's the Holder regularity. And I'm not going to say too much about displacement, but this displacement allows you to work with infeasible systems. So the displacement says we're actually talking about the distance, the minimum distance between the two sets. So this works for minimum distance as well. Okay. So this theorem says that as D increases, then the gamma, of course, is getting smaller, and then this becomes worse over here. Okay? So there's a constant, but of course the distance to the gamma, because the distance is going to be a small number, distance to the gamma would be bigger. Okay? So the Holder condition becomes worse as the singularity degree becomes bigger. So this is a recent paper of myself and Dima and Lee over here. So this is sort of giving you an idea of that there's something more to singularity degree than just regularization to get rid of Slater's condition. There's something hiding there. So this theorem holds, and also we did some empirical evidence, a lot of tests, which confirmed this little theorem here. So again, this is with displacement, so I'm not stating it with displacement, but this result is with displacement. But essentially it says, if we go and we apply the method of alternating projections, so this is essentially the old von Neumann method of alternating projections, okay, based on his work, okay, for STP, then if that sequence converges, and this is bigger than 0, so essentially Slater condition failed, then the rate is proportional to this constant over here. Okay, and again, you can see that this convergence rate slows down as D is increasing.
Henry,
yeah.
Can you please pronounce this bizarre word for me? CGNCE.
Convergence. Oh, yeah, I'm just safe space. Okay, any other questions? Okay. So a little summary of what I've done so far. So preprocessing is essential, as we discussed a little bit in the LP software. And the question is, can we do facial reduction in general? So I think some people here who are trying to do that in commercial codes for general problems. It's something very hard. A lot of preprocessing for LP is essentially facial reduction and works well. But for general problems, it's really hard. But you can really exploit structure. So there's many, many problems, as I mentioned right at the beginning, STP relaxation for QAP and for many other problems where you can exploit the structure and do this very, very efficiently. Okay? So I'm going to just quickly look at some other applications, especially matrix completion. Yeah, please.
The previous slide about the Sturm theorem, which Sturm theorem is a consequence of your convergence result? Or?
No, it's the other way around.
It's the other way.
Yeah. Sturm's theorem came in 2000. This is 2015. This is very recent.
Okay, yes. But
Yeah.
you cannot go the other, I mean,
Can you go the other way?
or
That's an interesting question.
I mean, by doing this and so in your theorem you assume it converges, you do not prove.
Yeah, we're assuming convergence. But we're not assuming that we're converging to something in the intersection. So there is this with displacement hiding that I just didn't want to get into details, but
Okay.
yeah.
And in the proof of Sturm theorem, the way you prove this inequalities, you give an explicit. How is that proof?
You mean
Yeah.
Sturm's theorem?
Is there an
No, I don't remember.
It's
Yeah.
a facial reduction. It's a facial reduction, hiding implicit.
Okay. I mean, because you need to produce a point X in the intersection that is close enough given.
Yes. Yeah. So in the proof, he wrote down that it was explicit.
Okay, so I'm going to repeat a few things that Nathan had in his talk. I know some people weren't there. Maybe I'll just modify a few things that he stated. So I'm looking at Euclidean distance matrix completion and sensor network localization. So everybody here, I think, knows this very well. It's an old problem. R is the embedding dimension for notation. N is the number of sensors. And M is the number of anchors that we have. And this is the notation for the pairwise distances, the ij component of the Euclidean distance matrix. This is the radio range telling us how many edges we have in the graph. This picture looks very familiar, very similar to Nathan's picture. So it's just a bunch of sensors there's an edge when it's close enough within the radio range. And these are the anchors. So we want to complete the picture, find all the edges that are missing. So what was interesting for us when we started working on this was the connections with graph realization and also Euclidean distance matrix completion. So there's people working in all these different areas, semi-definite programming, EDM, matrix completion, people working in the 80s and looking at completion problems for SDP and also EDM, who aren't here. And so it was interesting to see the connections for this. And the interesting thing for us was this essentially rigidity hiding in the background, though we never looked at the word rigidity. So we were just looking at cliques, and the anchors form a clique. And so Nathan had this slide as an equivalent slide where he showed how the distance matrix, the EDM, which is just the squared distances, if we expand, then it's just a linear transformation of B. B is just PP transpose, it's the Gram matrix. So this linear transformation K is generated in this way. There's the connection between positive semi-definite and EDM. Okay, so it's a very beautiful relationship. And this is some of the properties. So if we have a B positive semi-definite, then this is how to get the distance matrix, which what we did before. And there's a Moore-Penrose generalized inverse, which is very easily expressed from using this matrix J, which is a projection onto the orthogonal complement of the vector of ones. And the Moore-Penrose inverse of a distance matrix always gives you a semi-definite matrix that's centered. The row and column sums are 0. Okay. And this is Schoenberg's theorem all the way back in 1935 that relates the distance matrix with the embedding dimension, the positive semi-definite matrix. And if you factor it, then you get exactly the embedding dimension. Okay. So we've seen this many, many times already. So I'm just going to go on. So when Nathan and I when we started on this, we were trying to solve this as an SDP. Essentially something that looked like this. This is just a Hadamard product, element-wise product. And so we were just minimizing this as an STP. We thought, a very robust STP algorithm, not one of the public domain ones, one that was very, very good at solving hard problems, and we couldn't get more than 3-4 decimals accuracy, and it would take forever. We managed to get maybe 50 nodes done. And then we realized, sort of the way math works, I guess, you run into a headwind and you realize what's wrong, and sometimes it really changes things and helps things out. So we realized what was wrong, that this problem is highly degenerate. So Slater's condition just fails greatly, if that's the right word. So what happens is when you have a clique, okay, and if we use K-dagger to go back and look at the piece of the Gram matrix using a clique, then that rank is going to be found using the embedding dimension. Embedding dimension the rank has to be less or equal to the embedding dimension. So the rank of the full matrix is going to lose a significant amount. So the rank of the full matrix loses this amount over here. So the full matrix cannot be positive definite. Okay? So that sounds, and that's what was causing us to have so many numerical difficulties. And then we realized how to overcome this by using this facial reduction that Nathan described. So I'm going to go through this a little bit more quickly than I had originally planned. So you've seen for those of you who were here when Nathan presented his talk, you've seen something very, very close to this. You go and you take your clique, that corresponds to a block of the EDM. You apply K-dagger, you get a piece of the Gram matrix, and then you find a spectral decomposition. Once you find the spectral decomposition, you take the eigenvectors corresponding to the positive eigenvalues. You add this vector of 1s over here, and then you form this matrix by filling out with the identity. And then this gives you the minimal face that contains that clique. So there's an explicit expression for the minimal face. And this, of course, requires being centered. So by saying this intersection SC, it means that we want to center the problem, because the K-dagger always gives you a centered matrix. And this is equivalent to this formulation as well. This V does the centering for you. Okay? So this is an explicit linear algebra way of doing this clique reduction. Okay. And this is just how to do several of them. And then so that worked really well. So we did that around 2008 or so. And then the breakthrough was when we realized how to work with two cliques and to find the intersection of two of them. And so this result here just provides the intersection of two of them, because there's a range representation for each face. So all we have to do is find the intersection of ranges. So for each clique, we found a range. So we just have to find the intersection of two ranges, and that's going to give us the intersection of two cliques. So this is the linear algebra involved in that. Okay, so that's the geometry. So the geometry is over here with two cliques, and when we have two cliques, what we want to do is find the union of all the edges for the two cliques. And for the union of the edges of the two cliques, it's the intersection of two faces. And the intersection of two faces is found by taking the range representing one face, the range representing the other face, taking the intersection of two ranges. So that's what this is over here. And then what really made things work is we found a very efficient way of finding the intersection of these ranges. They had some very, very special structure. It needed to find this matrix here, which ended up being orthogonal. And so all we had to do is find it and do this multiplication, and we were able to find the intersection of the ranges. And because we're doing it with an orthogonal or rotation, we really were able to maintain a lot of accuracy. And then at the end, you've seen this as well. at the end, we rotated things back so that the anchors were in their right position with a Procrustes problem. So that's the algorithm. So I just wanted to show you some of the tests that we did in 2010. So this is the laptop that we were using. The embedding dimension was 2. We used this square region. We used 9 anchors. And we used this RMSD measure over here for the error. And so this is some of the results. The numbers may look a little different than what Nathan showed because he was dividing by R. He was dividing by R here, so his decimals weren't as high. But this is quite amazing that we would get 16 decimal accuracy for these large problems. And then we went up to 100,000 sensors over here with 9 anchors. There's the radio range. There's the accuracy. It took 9 minutes on a laptop in 2010. So we looked at the expected density of the graph. So this is the number of edges that we expected, and this is the number of nodes. So we're solving an STP with 77 million constraints and 5 times 10 to the 9th variables. So of course we're not solving the STP, but it's really, and we're getting 16 decimals accuracy. So this was a very unexpected and nice surprise. Okay, so I just want to go back and mention, because some of you may not be here when Nathan gave his talk. If we go back and just look at this exposed vector, I just want to remind you this view of the exposed vector. So there's our feasible set. It's just a feasibility problem. Then a vector V exposes a proper face of the image of the cone containing B, if and only if V satisfies this system. And this is our theorem of the alternative. And then, so this is what we're doing now is we're going to do the exposing vector approach. So we're going to find small faces on subproblems in the image space, and then use this little theorem to go back and find exposing vectors for the original problem. Okay? So this is the view with exposing vectors. So this is what Nathan described. And this is related, we found this out later, as Nathan mentioned, it's related to a paper of Amit Singer.
20 minutes.
Okay, thank you. That's perfect, okay. So this is the exposing vector approach. So we find an exposed vector for the small problem, and then we just fill it out with zeros, and we get this weight that tells us how good this exposing vector is, depending on the nice structure of eigenvalues. And then we just add this up, and as before, we get an exposing vector for the whole problem, and so we solve a much smaller STP. And so one of the things that happened using this exposed vector approach, for the first clique approach, the errors seemed to be adding up. As Nathan discussed, the errors grew, and we couldn't solve problems with a large error. However, here it's as if the errors cancel because you're adding these exposing vectors, so it's almost as if one error is canceling the other because we're just doing things with random noise, so we don't expect the random noise errors to keep adding up. So the problems we were able to solve here, and as Nathan showed you, had about 20% noise, and we're still able to get very, very good solutions. Okay, now this little part, I just want to quickly state this. I don't want to say this very much because Shinju is going to be giving a talk on Friday, and I think he's here somewhere, and he's going to provide much more detail, so I can save some time here. So this is PSD and EDM matrix completions, and it's the connection with chordality and completion problems. So it's been known for a lot of years, so this going back to the 80s, that chordality was a necessary and sufficient condition for positive definite completion, and with a little bit of extra work, then it's also true for positive semi-definite completion. And for EDM completion, it's if and only if the graph is chordal. Okay? So by completion, of course, it means that the small problems are EDMs. And for PSD, it means that the existing minors are non-negative. So what this little result says that if the graph is chordal, and we're looking at a completion problem, okay, and then we only use the cliques, then we get the minimal phase. Okay? So if you assume chordality, the cliques are enough. Okay? And the same thing for EDM. If you assume chordality and you've got a partial EDM, so all the existing submatrices are EDM, then chordality is enough to get the minimal phase using only cliques. And this in some sense explains why when Nathan and I were working, and also Amit Singer, why we were so successful. Because we only used cliques. We didn't use any other special, because there's a whole bunch of other rigid structures in the graph you think that you need, right? But we only used the cliques, and we still were able to get these really good results, right? Without ever, most of the time we never needed an SDP solver. Okay? So Shinji is going to talk about this and present an if and only if theorem plus a lot of connections, other results. So that's on Friday. So I'm being very quick with this. Okay. And this has to do with singularity degree as well. So if we assume chordality, then the singularity degree has at most 1. That's sort of what I'm saying. Okay, the last topic. So I've got maybe 15 minutes or so.
Yes.
Okay. So this is a little bit of a gamble. I was hoping there would be some experts in the audience. I know Pablo's here, so I hope. So this is a bit of a gamble because this is something which is sort of ongoing. So if you find something that I've done terribly wrong, please tell me. But I'm looking at low-rank matrix completion. So this is very often called compressed sensing. So we're given some matrix Z, and we want to find the completions. We want to find a matrix M of minimum rank, which is going to approximate Z, and E hat is the edges that we know, the elements of the matrix that we know. Okay? And the delta is a tuning parameter because very often there's noise in the data, so very often you don't know this problem completely. Okay? And what's used recently and has become very popular is the nuclear norm. Okay? So instead of minimizing the rank problem, which is a hard non-convex problem, Pablo and co-authors, Miriam Fazel and others, they've used this this nuclear norm as a nice convex approximation for the minimum rank problem. And this problem can be embedded inside of an SDP. So we can solve the minimum nuclear norm problem as an SDP. So if we take this Q and put the Z in these positions and put it over there, okay, and do the indices so that if they come from Y hat, so they correspond properly for this bigger matrix, then all we have to do is then minimize the trace of Y. There's a half missing here. It's not so important in the objective. And so this problem will be the same. And if there's no noise, then essentially Y E bar is equal to Q E bar is your constraint. Okay? So Y is positive semi-definite, but the diagonal is not constrained. We're minimizing the trace, right? So why include it over here in this talk? Because Slater's condition is always satisfied. Okay? So what we want to do, and this is some work these are the people I've been working with recently. So we want to exploit the structure at the optimal solution. Instead of exploiting the structure of the feasible set, we know something about the optimal solution. Right? So we'll take a look at the graph corresponding to this problem. And so we just take the node set, so we just add, 1 to m is, so the matrix Z was m by n, so originally we did it as a bipartite graph, and this is why I had asked you that question during your talk. But we just did it in this general larger embedding. And so the edge set for this graph is given over here, and the weights are just given by the data that we know. Okay. And so we have a graph, so we have a corresponding adjacency matrix. So we had adjacency matrix for our problem with cliques. So we can find cliques in here. Finding a clique here corresponds to a known submatrix of the data. Because if you did a row and column permutation, you can always move things so that you know this matrix X part of the data. Okay? So we can now do a full rank factorization of this X using an SVD. Okay? So it's just a full rank factorization. And then write down the optimality conditions. Okay? So if we expand, you'll see that the P dq transpose over here, this is the X, right? So that has to be the X. However, the P dp transpose is on the diagonal, and the Q dq transpose is on the diagonal. Okay? And what do we know about faces? Faces are determined by ranges. So from here, we can use the fact that the ranges have to be equal. Okay? So if we assume that the R, let's assume that we know, for now, the simple case that we knew the rank, we can now find exposing vectors using these two blocks over here, because we know the ranges for these two matrices using the full rank factorization. Okay? So we take those two matrices, we find exposing vectors, and then we fill it out with zeros the way we did in the EDM algorithm. To get exposing vectors, we can add them up. We get an exposing vector for the original problem. And then that's going to reduce the size of the problem the way everything happened before. Now, there's a lot of little tricks that happen here. What happens is that this big problem, let's say Z, well, you can see that some of these problems are quite large, right? That's a lot of numbers. So this problem means that the Y is huge, right? Well, typically after doing these exposing vectors, that huge Y became 10 by 10, 5 by 5, very, very small. Except the constraints stayed. There were 200,000 constraints. So we had this huge least squares problem. Have any of you been working with sketch matrices? No, so there's this, somebody, Wainwright came and gave a talk at Waterloo and told us about sketch matrices. It's quite an amazing phenomenon. If you have a least squares problem, which is very, very overdetermined, you take a random matrix with a few rows, but of course the same number of columns, and hit it on the left with this random matrix and solve the new least squares problem. Most of the time, you do really, really well. You do almost as well as solving the full least squares problem. So that's what we did here as well. So we had this problem which is really narrow, but a huge number of constraints, and we ended up solving this small least squares problem. So the results are almost too good to be true, so you probably shouldn't believe them. I know if you can see them. I usually come up with slides that nobody can see. Can you see them? Yeah. So you can see that the rank, we started rank 2. We even got rank 2 small down here on the average. So there's 5 instances in each row. this is the times. The times were like negligible, really, really small. And these are the residuals. So the first row was no noise, and we ended up solving the problem without any noise. So the results are a bit too good to be true, so I wouldn't believe it. Yeah.
Do you have to do a search to find which subblocks are known, or which principal minors are known? That can be a hard problem.
Well, it's just as hard as finding cliques for our EDM, right? It's the same problem.
Yeah, okay, same question. Isn't that very hard?
It's hard. Well, what we did,
It's hard in general.
yeah. Well, we did, but we don't have to find the big. We don't have to find the big cliques. In fact, you don't want to find big cliques because each time you find a clique, you want to find an eigenvalue decomposition. So it's good to find a lot of small cliques and then use that fact that when you add them up.
So how do you find them?
We used logical variables and a bunch of little tricks and a lot of Nathan's tricks.
But rather geometric abstraction really helps to find
Yeah.
these links.
But it was just heuristics.
Roughly you pick a node that's neighbors to all the current nodes in your clique and you add it.
Yeah, if you have rows of a matrix, you make them logical in MATLAB, and you can just add, and then you can find out. Yeah.
I think the greedy method can always reach the optimal smallest deduction, optimal deduction. We don't have to always find the optimal clique, but we can just find the. There is
Oh,
no
sorry.
Suppose you want to find all 5 cliques, not maximum, all 5 cliques. You don't find all of them.
I think you just try to
Fifth.
find the non-trivial clique deduction repeatedly, and you can find any.
Output potentially.
Yeah. Pablo.
So here, I mean, doesn't this work because the rank is very small? I mean, somehow in the typical.
Yeah, bigger rank makes it harder. So, but we did do bigger rank as well, 3 and 4. But you're right, it didn't work as well. Yes, very true. So you think it won't work for large rank?
I mean, the thing is, in the situation where the rank is large or a significant fraction of the matrix,
Right.
like log n or something like this, then you will never have also like a full, you will never observe a clique of that size.
Right. So we have a little lemma, which is sort of obvious from the lower semi-continuity of rank, that if the rank of Z is 5, then generically, if your matrix is at least 5 by 5, right, then it's generically going to be rank 5. So yes, if the rank is large, then it's going to be much harder to find those cliques. Definitely, yes.
But he's saying for sparse sampling, there won't need to be any cliques of that size.
But for rank 2, it worked.
Well, that's still not pretty right. That row is like 40% of the entries, right? Is that what that means?
Yes, that's right, and that's true as well. Yeah.
So that's a pretty high percentage to some people.
That's true. Yes, I should have mentioned that.
Are these
yeah.
random instances?
Yeah, everything is random, done very quickly. So
So you
I'm
might
saying take it with a grain of salt.
the random. Are you using this matrix sketching? So the pre-multiplication by random matrix. Is that what you're using here?
to generate the random Z.
To generate, no, to solve the problem, to solve the least squares problem.
I'm using the sketch matrix. Yes.
So you want to watch out because with random matrices, these random methods sometimes exhibit like an unusually good behavior.
So I'm seeing good behavior because I'm being lucky.
No, I'm just saying that if you take like a matrix that isn't random but has been generated because of an application that has some, I don't know.
No, the sketch matrix is supposed to be random.
Yes, but your instances.
Oh, the instances,
saying-
yes, are random, and that's why it's behaving so well.
I'm not saying it's because it's.
But it's one of the reasons.
It
Yes.
could be. I'm
Well,
saying it is. It could.
we're depending on them being random because if it wasn't random, then the lower semi-continuity of rank wouldn't give us that cliques generically will have the right
But
rank.
if you want to complete a matrix, usually somebody gives you the matrix.
Yeah. So one of the reasons I posted this was just the fact that facial reduction is not only for the feasible set, that you can actually take advantage at the optimum, unless I've done something wrong in the theory as well. So that's sort of the main reason. And if I get any more feedback, that would be great. So this is really just ongoing. Thanks. We will try higher rank. And lowering the P. Yeah. Yeah, it'll be much harder. Any other questions? Thanks a lot for the question.
You're done?
Except for the conclusion.
So why don't you do the conclusions, and then we'll ask you some questions maybe.
Okay. Yeah, so though strict feasibility holds generically, failure, just like the differentiability case for optimization, which holds generically, failure seems to appear in many, many applications. And this facial reduction seems to be something which is not only useful to get rid of Slater and to get Slater and help in numerical methods, but it seems to be very useful in all sorts of theoretical ways as well. And as I mentioned, the one thing I didn't have time, is to show you how facial reduction just fits in so well with an ADMM type approach. It's really quite surprising. So we redid all the QAP-lib problems using this approach, and we improved all the bounds in the QAP-lib problem using this facial reduction approach by doing ADMM, because we could now use non-negativity and lesser equal to 1 constraints, which is something that's very hard to do with SDP. And the other thing is, this is something new that I haven't seen before, exploiting the structure at the optimality conditions. So if I got the optimality conditions correct, I think probably one of your papers, I'm not sure. But if I got that correct, then it seems that maybe there's other kinds of problems where there's very, very special structure at the optimality conditions that you can exploit. And then the problem can become a lot smaller. So thank you very much, and thanks a lot for the questions.
You can go on grilling him now. It's okay. Please.
Suppose you have this low-rank matrix completion, you're given data, and you go along with your algorithms and you process, and all of a sudden something goes wrong. Can you narrow where the contradiction is?
Well, when you say something goes wrong, I guess you mean I get a clique and the rank is too low? Because
Whatever.
if it's not random data, that could happen.
Somehow you get something that has a hole and it fails.
Yeah, so one of the things we should be checking is when we find a clique, then we get the corresponding matrix, that the rank. So the other thing is that I'm assuming is that I have an idea of the target rank. If I don't have an idea, then I got to start high and then start working my way down. How low can I go with the rank? There's still several open questions with this approach in the exposing vector. And so one of the things that went wrong early was it failed and we didn't understand why, and we still don't understand. I cannot use the P and the Q block in the middle together. I've got to use the P block by itself and the Q block by itself. So it's almost as if it's bipartite graph that I'm doing, and I can't use the two pieces together. And so the final rank of Y is double of what it should be. So I got to be careful there. But what else can go wrong? Yeah.
Pablo, did you?
Can you say something about the relationship between the singularity degree and like the Ramana duals? I mean, is that like really
About the what?
the singularity degree and the Ramana dual? Right? So that's like this singularity degree is number of.
So there's a paper that I wrote with Levent Tansel. So we proved the Ramana dual, that there's a way of translating the two in like a dictionary. So they really are equivalent steps. So the Ramana dual requires steps, and it'll be the same steps, number of steps. So the singularity degree means that at every step, you're actually finding the max rank exposing vector. And so there's an equivalent statement for the Ramana dual. And so his singularity degree will be exactly the same.
Anyone else?
Thank you.